Hello, and thank you for joining me today as we discuss potential energy. We continue our discussion on work, power, and energy. Today we're going to talk potential energy. The world around you is full of energy. All sorts of different energies are present, and so even a rock sitting on top of a mountain has energy because it could go downhill. Energy, by definition, is the capacity or ability to do work. Wowzers, that's not what I wanted. Let's try this. Energy is the capacity or ability to do work. And so again, work is moving an object a certain distance. So if a rock rolls downhill, that's doing work. So a moving mallet has energy that can be transferred to the puck, which raises against gravity to hit the bell, which is up here. Work is being done. Whenever work is done, so as long as you have work happening, energy is transformed or is transferred from one system to another. And we'll talk a little bit more about that. Work is only done when objects change position or have motion. Energy, though, can be present in objects at rest. That's what we're going to talk about today. So we can calculate energy for both objects at rest and in motion. We'll get to the motion part later on. And one last piece from this. It's measured in joules. So energy is in joules, capital J. All right. When you stretch a rubber band, so if you ever fling a rubber band across the room, when you stretch the rubber band, you're doing work because you're moving it. Energy is used to stretch the rubber band and is stored in that elastic until you let it go. When you release, it flies from your hand. So where is that energy stored between you stretching and releasing it? That is called potential energy. So this is your first or second term, I guess. Potential energy is a specific form of energy. It is the energy an object has because of its position, shape, or condition. Okay? And so this is our potential energy. So any object that is stretched or compressed to increase or decrease the distance between parts has potential energy. That's your elastic. Things like shocks on a bike or shocks in a car. That's elastic potential energy. And bungee cords, same kind of idea. Today, we're going to talk about things like if you're on a roller coaster and you get to the top of the first hill. You know, if you've ever been to an amusement park, typically the roller coasters, the very first hill is the biggest. And that's because that stores all your energy. So your position above the ground can give you energy that can move the coaster the entire way. And so, like the universal law of gravitation said, any two objects that have gravitational attraction towards one another, any two objects that have mass have gravity. This gives you gravitational potential energy, and that's going to be what we focus on today as far as energy goes. And so that form of energy, gravitational potential energy, depends on both mass and the height or the distance between those two objects. So an apple at the top branch of a tree has more gravitational potential energy than an apple on a lower branch because it's farther from the earth. But if two apples of different masses are the same height, the heavier one has more energy because it's heavier. So your equation for potential energy is mass times gravity times height. I always write it out. I have two sets of three. So I have GPE for gravitational potential energy equals mgh for mass, gravity, and height. Notice, if you have mass times gravity, gravity is an acceleration. So we did mass times acceleration is equal to a force, if you think way back. So potential energy is also equal to force times distance or force times height. Oops, that was the wrong letter. And this force times distance, that was our work equation. So notice how all of that comes together. And that's how these all are conjoined. All right, so the height of the object is relative to a certain point, usually from the ground, but not always. For example, if an apple were about to fall into a bird's nest on a branch below the apple, the height above the nest would be used to calculate the potential energy, because once it gets into the nest, it's going to stop falling. Let's do some practice questions. So for starters, I have a 65 kilogram rock climber ascends a cliff. Ascends means climbs. What is his gravitational potential energy at a point 35 meters above the base of the cliff? So I know a couple things. One, I'm looking for gravitational potential energy. So I need to know GPE. To do that, I need to know a mass, I need to know gravity, I need to know a height. Well, it said my mass was 65 kilograms. So let's make sure we write that down. Our height is going to be 35 meters. And gravity, we have to think back, is 9.81 meters per second squared. So if I use my equation, GPE equals mgh, I can then substitute and say GPE equals 65 kilograms times gravity times 9.81 meters per second squared times my height, which was 35 meters. If I take 65 times 9.81 times 35, I should get an answer of 22,317.75. 22,317.75. Looking at my question, I have 2 sig figs here and 2 sig figs there. I need 2 significant digits, so I'm going to round this to 2. So I'm going to have 22,000. Remember, my unit is joules. Or I can abbreviate this, and I can say this is 22 kilojoules, because kilo means 1,000. So either one of these two answers will work for this question. All right, question 2. A diver has 3,400 joules of gravitational potential energy after climbing up a diving platform that is 6 meters above the, it's supposed to be water. What is the diver's mass in kilograms? All right, so things that I know. 1, I'm looking for mass. So mass equals question mark. GPE of this diver is 3,400 joules. I know that my gravity is still going to be 9.81, unless I tell you it's not on Earth. We're going to go with that number. I know that my height, which was stated there, is 6.0 meters. Now my equation, GPE equals mgh. I need to solve for m, so I'm going to divide both sides by gravity times height. So I get mass equals GPE divided by gravity times height, which means if I do numbers, I have 3,400 joules divided by gravity, which is 9.81 meters per second squared, and my height was 6.0 meters. So if I take 9.81 times 6, that gives me 58.86. So this is another way of saying divided by 58.86. So if I take 3,400 divided by that answer, I should get 57.8, and because I have 2 significant digits here, we'll go with 58 kilograms. So 58 kilograms on that one. All right, I'm going to give you a chance to practice a little bit of this. So if you will pause this video, I'll read through these and then pause the video. So calculate the gravitational potential energy of a 65 kilogram climber on top of Mount Everest. Has a height of 8,800 meters. And the second one, calculate the gravitational potential energy of a 0.52 kilogram bird flying at an altitude of 550 meters. Work through both of those, pause this video, and then when you resume, you'll get your answers. Okay, so for the first one, we should have had 5,600,000 joules, or 5.6 times 10 to the 6th joules for the gravitational potential energy of the climber. And the bird had a potential energy of 2,800 joules, or 2.8 times 10 to the 3rd joules, or 2.8 kilojoules. All right, let's do 2 more. So here's another set of practice questions. Again, I'll read through these, pause the video, and then you can try them on your own. So calculate the GPE of a 1,200 kilogram car at the top of a hill that's 42 meters high. And the last one, a science student holds a 55-gram egg out a window. Just before the student releases the egg has 8.0 joules of gravitational potential energy with respect to the ground. How high is the student's arm above the ground in meters? Note at the bottom it says, hint, make sure your mass is in kilograms. All right, go ahead and pause this video. When you resume, you'll get your answers. And we should have 490,000 joules for the first one, and your height should have been 14 meters for the climber. Here are some review questions, so you should be able to answer, what does gravitational potential energy depend on? There's 2 things. I need to know the units for gravitational potential energy, And I want to know what happens to the energy if the height of the object doubles. What if its mass doubles? Make sure you can answer those questions, and I look forward to working with you as we continue this discussion.